Hey fellow nerds, today we are going to discuss the common source configuration of MOSFET amplifiers. We'll be covering the common source configuration, its small signal model, voltage gain, input impedance, output impedance, and some biasing techniques. Let us start by understanding the common source MOSFET amplifier. In this configuration, input is applied between the gate and the source. Output, on the other hand, is taken between the drain and the source. We have also applied V0 over here, which will make sure our transistor is in saturation mode and we can use it as an amplifier. Along with that, we have applied V1 over here to provide the necessary power for the circuit. Now, let us try to represent the same circuit in a much simpler way like this. You can see that in the new representation, instead of calling this V1, we are calling it VDD. It is the supply voltage we are connecting at the drain. From now, we'll be using this representation of the circuit. Let us start by understanding how this circuit does the amplification of a signal. Let us assume that the input Vin is a sinusoidal signal and it looks like this. Along with that, we have also given V0, which is the bias voltage. So ID, the drain current, is going to have two components. One, a DC component because of V0. Two, an AC component because of Vin. So we can represent ID as ID0 plus GMVin. ID0 is the DC component, GMVin is the AC component. Why is the AC component GM multiplied by Vin? We have actually discussed this in the previous video, so if you don't remember, please go and watch it. Now, I want to plot VRD, which is the potential drop that we get across the resistor RD. It's pretty easy because RD is a resistor through which a current ID is passing. So according to Ohm's law, the voltage across RD is IDRD. Since ID is ID0 plus GMVin, VRD is going to be ID0 RD plus GMVin RD. Here again, ID0 RD will be a DC component because ID0 is DC and RD is just the resistance. On the other hand, GMRDVin is going to be an AC signal because RD is again just the resistance and GMVin is AC. So VRD, or the potential across the resistance RD, is basically a DC component plus an AC component. Let us now try to plot this on a graph. First, I want to plot just GMRDVin. It is the input multiplied by GMRD. So we'll get an amplified version of the input. Now we have to add ID0 RD to it, which is a DC value. So the graph will finally look like this. Finally, I want the output. You can see that we are applying VDD over here, out of which IDRD will be dropped across RD. The rest will come out as the output. So V output is VDD minus IDRD. But IDRD is ID0 RD plus GMRD Vin. So we can write it like this. V out is VDD minus ID0 RD minus GMRD Vin. Here VDD is a DC value. Minus ID0 RD is also a DC value. But minus GMRD Vin will be an AC value because we have Vin. Vin is sinusoidal. Therefore, in this case, this whole thing is going to be the DC value and this will be the AC or sinusoidally varying value. Let's try to plot this on a graph. First, I will plot negative of GMRDVin. It is the negative of the input multiplied by GMRD. It is an amplified version of the input which is also inverted. So it will look like this. Where input had the positive half cycle, output has the negative half cycle. We also have to add the DC value VDD minus ID0 RD. If we do that, finally the graph will look like this. Final output of our amplifier. Let us now figure out the small signal model of our common source amplifier. For that, the first thing we need is the small signal model of a MOSFET. So let us bring that. Now, as the name suggests, in the small signal model, we only need the small signals. Here the input Vin is a small signal. V0 is not a small signal. VDD is also not a small signal. So we have to remove V0 and VDD. To remove a voltage source, we have to short it. Why? Imagine you have a point A over here and a point B over here. To make sure the voltage between these 2 points are 0, we have to short them. Now imagine you have a point A over here and a point B over here. To make sure the current flowing between these points is zero, we have to open the circuit. So to remove voltage sources, we have to short them, and to remove current sources, we have to open them. So in the small signal model, at the drain, we'll have V input, which will go to the ground, like this. Also, at the drain, we have RD, which is actually connected to VDD. Now, VDD can be represented by something like this. We have VDD, which goes to the ground. When VDD is shorted, the other side of RD will directly go to the ground. We have already seen that we call this the AC ground. We can show that in the small signal model like this. Now, output is taken at the drain. Let us also show that. What we have over here is the small signal model of a basic common source MOSFET amplifier. Let's take the first case, where the channel length modulation is ignored, which means channel length modulation coefficient lambda is 0. We'll start with the voltage gain. For that, the first thing we need is the small signal model. Over here, you can see that Vin is applied between the gate and the source. So VGS is going to be equal to Vin. In that case, we can write GMVGS is equal to GMVin. The current we have over here, GMVGS, is actually equal to GMVin. Now, take a look at RD. RD is grounded on one end. On the other end, it has a potential that is equal to the output voltage. So the net potential drop across RD is V out minus 0, which is V out. Then according to Ohm's law, the current that is flowing through RD will be V out divided by RD. Let us show it over here. Now let's apply Kirchhoff's current law at the drain. We have two currents. One is V out by RD flowing out of the node. The other is GMVGS, which is also flowing out of the node. According to the law, their sum has to be equal to 0. GMVGS plus V out by RD should be equal to 0, or we can write GMVGS should be equal to negative of V out by RD. Now over here we found GMVGS is equal to GMVin. So we can write GMVin is equal to minus V out by RD. What we want is the voltage gain. Voltage gain is V out by Vin. From here we can easily write it. It is minus GMRD. Voltage gain is minus GMRD. Let's put it in a box. The next thing we have to find out is the input impedance of the circuit. For that, again, we need the small signal model. While discussing BJT amplifiers, we have discussed two cases where we can find input impedance. One is when there is no dependent source in the circuit. The second one is when there are dependent sources in the circuit. In our case, we obviously have a dependent source. The current source GMVGS obviously depends on the voltage we have over here, VGS. In such a case, the first thing we have to do is shut down all the independent sources. The only independent source we have is Vin. Since it is a voltage source, to shut it down, we'll have to short it. Then the gate will directly go to the ground like this. Again, what we have to find out is the input impedance. So what we have to do is apply a potential Vx over here and find its relation with the current Ix that will be flowing like this. It can clearly be observed that the circuit is open between these 2 points. That means current Ix cannot flow. Vx is the potential dropped across these 2 points. Since the circuit is open between them, we can say the resistance between these 2 points has to be infinite. That makes sense, but it is not entirely true. Because we actually can have some capacitance between these 2 points. And that will give some capacitive reactance. We know Xc or capacitive reactance is given by 1 by omega C. It is inversely proportional to the input frequency. So if omega is very low, that means Xc will be really high. If omega is really high, then Xc will be really small. In which case do we have to consider Xc? For low frequencies, we can see that the reactance is really high, so we can say the impedance is really high, even infinite. But for higher frequencies, reactance will have a reasonable value which we will have to consider. So to accommodate this idea, let us write down that input impedance is really high at low frequencies. Ideally, it will be infinite. Let us now figure out the output impedance. Again, we need the small signal model. Since we have a dependent source over here, first thing we have to do is shut down all the independent sources. The independent source we have is V in. If we shut it down, gate will be directly grounded. Now, what we have to find out is the output impedance. So we have to apply a potential Vx over here at the drain from where we are finding the output and find the relation of Vx with Ix. The first thing we have to see here is that the gain through the ground is directly connected to the source, which means the potential difference between the gate and the source is 0. VGS is equal to 0. If VGS is 0, then what is GMVGS? Also 0. That means no current is flowing over here. In that case, we can say that all of Ix has to flow through RD itself. And the potential across RD is Vx. So by using Ohm's law, we can write Vx by Ix should be equal to RD. Vx by Ix is our output impedance. So we can write output impedance is RD. Let's take the second case where the channel length modulation is included. Lambda is not equal to 0. We'll find the voltage gain first, for which we need the small signal model. Since channel length modulation is to be included, we'll have to add a resistance over here, R0, between the drain and the source. Since source is grounded, we can show it like this. Now, R0 and RD are in parallel with each other. To make it simpler, let us replace these two with one single resistor whose resistances are not parallel to RD. Now, this looks exactly like our old small signal model, except instead of RD, we have R0 parallel to RD. So the derivation will look exactly the same. The first thing we have to write is this: Vin will be equal to VGS. If Vin is equal to VGS, then GMVGS will become GMVin. Next, we'll apply Kirchhoff's current law at the drain. There are two currents. One is GMVGS flowing out of the node. Second will be the current flowing through the resistor R0 parallel to RD. The potential across it is V out. So the current will be V out divided by R0 parallel to RD. According to the law, their sum should be equal to 0, or GMVGS should be equal to negative of the current flowing through this resistor. Again, since VGS is Vin, here we can replace VGS with Vin. That gives us GMVin is equal to negative of V out divided by RD parallel to R0. What we want is the voltage gain, which is V out by Vin. We get it as negative GM multiplied by RD parallel to R0. Let's put this in a box. So basically, voltage gain is negative GM times whatever is the equivalent resistance we have between the drain and the AC ground. Now, what will be the input impedance? You can see that the input side of the small signal model is exactly the same as before. So including channel length modulation is not going to change the input impedance. It is going to be infinite at low frequencies. How about the output impedance? When we only had RD over here, output impedance was RD. Now we have R0 parallel to RD, which means even without doing the mathematics, we can say that the output impedance is going to be R0 parallel to RD. Let's go to the third case. I am going to remove RD. We do not have RD over here, but we need drain current, which I am representing using a current source. We have to find the voltage gain, for which we need the small signal model. So let us make that first. I'll start with the small signal model of a MOSFET. We have Vin at the gate. Since V0 will be shorted, we can show it like this. Now, what happens to ID? ID is a current source, which we have to remove because it is not a small signal. We already discussed, to remove a current source, we have to use open circuit. If the circuit here is open, then drain is not connected anywhere. But as you can see, lambda is not equal to 0, which means we have to include R0. R0 will be connected between the drain and the source like this. Output is taken from the drain, so let us show it. Again, do we really have to do the mathematics here? This looks exactly the same as our first small signal model, except instead of RD, we have R naught. Then what will be the voltage gain? With RD, we got minus GM RD. With R naught, we'll get minus GM R naught. Voltage gain is minus GM R naught. An important observation we can make here is that GM and R naught are both intrinsic properties of the transistor. And because of that, we can say minus GM R naught is the intrinsic gain of the MOS device. Again, since nothing has changed in the input side, input impedance is still going to be infinite at low frequencies. How about output impedance? When we had RD here, output impedance was RD. When we had RD parallel to R naught, it was RD parallel to R naught. Now we only have R naught, so obviously output impedance is R naught. In all the cases that we discussed, we saw that the voltage gain is directly proportional to the transconductance Gm. But Gm depends on factors like temperature and bias conditions, which means any variation in those will directly impact the gain. So we need a way to make sure the voltage gain is less dependent on the transconductance. For that, we introduce a small trick, degeneration. All we have to do is add a resistance at the source like this over here. To make it simple, I have taken lambda to be 0. That means channel length modulation is ignored. Let's find the voltage gain, for which as always we need the small signal model. It will look like this. The only extra thing we have is Rs, the resistor at the source. Now let us mark some things. If you take a look at Rd, it has the potential V out on one side and 0 on the other side. So the net potential is V out. Then according to Ohm's law, the current flowing through it is going to be V out divided by Rd. Let us show it over here. Now we have GM-VGS over here. Its direction is taken to be like this. So we can assume it is flowing like this and then it has to flow through Rs like this. If current through Rs is in this direction, we can assume Rs has positive potential here and negative here. Let us start by applying Kirchhoff's voltage law in the input loop, which is this one. I'll start from this point and go clockwise. As I go, I have V in from negative to positive. As I further go on, I have VGS, which is from positive to negative. So I have to write minus VGS. As I further go on, I have the potential drop across Rs also from positive to negative. So I'll have to write negative of the potential across Rs. Now, what is the potential across Rs? Current flowing through Rs is GM-VGS. So according to Ohm's law, the current will be GM-VGS multiplied by Rs. So let us write minus GM-VGS multiplied by Rs. Now, according to Kirchhoff's voltage law, the sum should be equal to 0. From this equation, we can write VGS in terms of V in. VGS is V in divided by 1 plus GMRS. Let it be there. Take a look at the node over here. There are two currents. One is GM-VGS going out of the node. The other is V out by RD also going out of the node. According to Kirchhoff's current law, the sum should be equal to 0. That means GM-VGS plus V out by RD should be equal to 0. Then we can write V out should be negative of GM-VGS RD. But what is VGS? It is V in divided by 1 plus GMRS. Let us replace it with that. That gives us this. What we have to find out is the voltage gain, which is V out divided by V in. From here we can easily write that. It is negative GM multiplied by RD divided by 1 plus GMRS. Let us divide the numerator and the denominator with GM. Then we can write the equation like this. Negative RD divided by 1 by GM plus RS. This is the voltage gain. Let's put it in a box. I hope you didn't forget why we added Rs in the first place. We wanted to make sure the voltage gain is not dependent on the transconductance Gm. But you can see that in the new expression we still have Gm, but it is less significant. Why? Let me show you. In the denominator we have 1 by Gm plus Rs. Now assume that we designed the circuit such that Rs is very much greater than 1 by Gm. Then 1 by Gm plus Rs, we can assume it is approximately equal to Rs itself because 1 by Gm is very small. In that case, the gain will approximately simply be negative Rd by Rs. That is how we have made the voltage independent, almost independent of Gm. But this circuit still has a problem. It is that its gain is going to be much lesser than the previous cases. Minus Rd by Rs is going to be less than minus GMRD, which used to be our gain before adding degeneration. That will be another problem we have to solve. But before that, let us figure out the input impedance and output impedance of the circuit. For that, again, we need the small signal model. Since we have a dependent source in the circuit, the first thing we have to do is shut down all the independent sources, which means Vin has to be shut down. Now, what we want is the input impedance, so we have to apply Vx over here and find its relation with Ix. Well, this is again very similar to what we did before. The circuit is open over here, which means impedance has to be really high. But then we also have to consider the capacitance that can be there. So we will write at low frequencies, input impedance is really high or infinite. Let us see the output impedance, for which again we need the small signal model. We have to shut down Vin. Now, what we need is the output impedance, which means we will connect Vx over here and find its relation with Ix. Let us start by marking the current flowing through our resistance Rd like this. I'll call it I0. Consider this node. Ix is coming into it. I0 is also coming into it. GmVGS is going out of it. So according to Kirchhoff's current law, Ix plus I0 should be equal to GmVGS. Now consider this loop. We have two potential drops. One is VGS, the other is potential across Rs, VRS. According to Kirchhoff's voltage law, their sum should be equal to 0. VGS plus VRS should be equal to 0, or VGS should be equal to negative of VRS. Now, VRS is the potential drop across the resistor Rs. According to Ohm's law, it is the product of Rs with the current flowing through it. Current flowing through it is GmVGS. But GmVGS is Ix plus I0. So we can say VRS is Ix plus I0 multiplied by Rs. Over here in this equation we have VGS. Let us replace it with negative of Ix plus I0 multiplied by Rs because that is equal to VGS. Then we get this equation. Ix plus I0 is minus Gm multiplied by Ix plus I0 multiplied by Rs. Let's open the bracket. That gives us this. Let's take Ix and minus Gm Ix Rs on one side of the equation, I0 and minus Gm I0 Rs on the other side of the equation. This can be written as Ix multiplied by 1 plus Gm Rs. This can be written as negative of I0 multiplied by 1 plus Gm Rs. That means we can cancel 1 plus GMRS from both sides of the equation, which gives us Ix is equal to negative of I0. Now, potential across Rd is Vx. Current through Rd is I0. So according to Ohm's law, potential across Rd is I0 Rd. So is Vx equal to I0 Rd? Not exactly, there is a slight difference because we have taken the direction of current I0 to be like this, which means positive potential is here and negative potential is here. But for Vx, positive is here and negative is here. So we'll have to write Vx is equal to negative of I0 Rd. Now, what is negative of I0? It is Ix. So Vx is Ix Rd. What we want is the output impedance, which is Vx by Ix. From here we can see it is Rd. Output impedance is simply Rd. Now, how about we include channel length modulation and lambda is not equal to 0? For that, again we need the small signal model. I have shorted the input. I have also added Vx at the output. Now, to show channel length modulation, the one thing we have to add is a resistance R0. R0 is always connected between the drain and the source. So here we'll have an extra resistance R0 connected like this. Now we have to find out Vx by Ix and that will be our output impedance. Here, finding it directly using mathematics is going to be complicated. So I am going to use a trick that we have used before in BJT amplifiers also. We are going to ignore RD first, find the equivalent resistance of the rest of the circuit, and then reintroduce RD. If we ignore RD, the small signal model will look like this. Let us take a look at the input loop, which is this one. We have two potential drops. One is VGS, the other is potential across RS, VRS. According to Kirchhoff's voltage law, the sum has to be equal to 0. That means VGS plus VRS should be equal to 0, which means VGS should be equal to negative of VRS. Now, what is VRS? VRS, according to Ohm's law, is RS multiplied by whatever is the current flowing through it. You can see IX is flowing like this. It will split into two at this node. But it will again combine over here. So basically the current flowing through RS is still IX. That means according to Ohm's law, potential drop across RS is IX multiplied by RS. So VGS is negative of IXRS. Now let us apply Kirchhoff's voltage law in this loop. I'll start from the ground and go anti-clockwise. First I have Vx from negative to positive. Then I have R0 over here. What will be the potential drop across R0? For that we need to know what is the current flowing through R0. Ix is coming into the node out of which GMVGS flows through here. That means Ix minus GMVGS will flow through R0. So potential drop across R0 is Ix minus GMVGS multiplied by R0. Since current is flowing in this direction, potential across R0 will be positive here and negative here. This is the opposite as that of Vx. So I have to write negative of Ix minus GMVGS multiplied by R0. Again, as we go on, we have Rs. Potential drop across Rs is also positive here and negative here, opposite to that of Vx. So we'll have to write negative of Vrs. But negative of VRS is negative of IXRS. So we can write it over here. According to Kirchhoff's voltage law, this whole sum has to be equal to 0. Now, over here we have a VGS. But VGS is minus IXRS. Let us replace it with that. You can see all these terms have IX in it. Let's take them to the other side of the equation and take IX as common. That gives us Vx is equal to Ix multiplied by R0 plus GMRS R0 plus Rs. What we want is Vx divided by Ix. Now, what is this? This is the equivalent impedance of the rest of the circuit when Rd is ignored. That means we can model the rest of the circuit ignoring Rd like this. Let us now introduce Rd. What will be Vx by Ix in this case? It's very simple. All we have is these two resistances in parallel to each other. So the equivalent resistance is going to be Rd parallel to 1 plus Gm R0 multiplied by Rs plus R0. Let us now go back and solve a problem we had. We saw that when we added degeneration, the circuit does become less sensitive to Gm, but gain becomes lesser, which is not something we want. To make sure that degeneration does not affect our gain, this is what we do. We will add a bypass capacitor. We'll add a capacitor in parallel with Rs at the source of the MOSFET. How does this help? Let us see. For that, consider the small signal model. The only extra thing we have is the capacitor Cs in parallel with Rs at the source. Now, what happens to Cs in the small signal model? We know capacitive reactance Xc is given as 1 by omega C. C is in the denominator. Capacitive reactance is inversely proportional to the capacitance. Here, since the capacitance value is high, capacitive reactance is going to be very low, and hence we can replace this capacitor over here with a short circuit like this. Which means in the small signal model, Rs is being shorted. Source is directly grounded. So we can simply draw the small signal model like this instead. We don't need to show Rs because it is shorted. But then this is the exact small signal model we had before adding degeneration. In this case, the gain is going to be minus GMRD, which is our original gain, which means degeneration is not affecting the gain anymore. So the only thing we have to do to make sure that RS does not affect our gain is to add a bypass capacitor. So far we have seen that the gain of the amplifier depends heavily on the load resistance. But what if we do not want to use a plain resistor? What if we want something better, something that fits nicely on a silicon? That's where the diode-connected MOSFET comes in. It is just a MOSFET with its gate and drain tied together. We can represent it like this. You can see how the gate is shorted with the drain. Let's do some analysis, for which obviously we need the small signal model. We'll start by taking the small signal model of a MOSFET. The only thing we have to do is short the drain and the gate like this. Output is taken at the drain. So let us try to find out the impedance seen at the drain. For that, I will take the small signal model and connect Vx over here and find its relation with Ix. Here, gate is directly connected to the drain. Through the ground, source go over here, which means potential between the gate and the source is actually just Vx. We can write Vgs is equal to Vx. Now, Ix flows like this and then it has to flow like this. Why? Because the circuit is open over here. So Ix is basically equal to GM-VGS, but VGS is Vx. So we get Ix is GM-Vx. What we want is Vx by Ix. It is clearly 1 by Gm. So the diode connected load is equivalent to a resistance of 1 by Gm. What if channel length modulation is included? In that case, we'll have one more resistance R0 between the drain and the source, like this. Let's apply Kirchhoff's current law at this node. Ix is coming into the node. Out of that, some current has to flow through R0. How much will that be? R0 has a potential Vx across it. So the current flowing in this direction will be Vx divided by R0. Also, GM-VGS is flowing out of the node. According to Kirchhoff's current law, the sum has to be equal to 0. So we can write Ix is Vx by R0 plus GM-Vx. Why GM-Vx? Because we can see that VGS is basically still Vx. Now, on the right hand side, we have Vx multiplied by 1 by R0 plus Gm. What we want is Vx by Ix. It is easily 1 by R0 plus Gm. What is 1 by R0 plus Gm? Assume we have a resistance 1 by Gm. We have another resistance R0 and they are in parallel with each other. What will be the equivalent resistance? Equivalent resistance will be 1 by reciprocal of the first one, Gm, plus reciprocal of the second one, 1 by R0. This is exactly what we have over here. So this is basically R0 being parallel to 1 by Gm. So the impedance seen at the drain is 1 by Gm parallel to R0 if channel length modulation is included. If it is not included, it is simply 1 by Gm. Let us take an example. Consider lambda is equal to 0, so we do not have to consider the channel length modulation. This is the circuit we have. Instead of RD, I have used a diode connected load. Let's try to find the gain. We just saw that a diode connected load as seen at the drain is equivalent to a resistance of 1 by Gm. Since we are calling the MOSFET M2, we can say the equivalent resistance is 1 by Gm2. We can model the entire circuit like this. Now this is a normal common source amplifier. In place of RD, it has 1 by Gm2. Now what will be the gain? If we had RD, the gain would be minus Gm RD. Gm would be Gm1 because the MOSFET here is called M1. So here the gain is going to be minus Gm1 multiplied by 1 by GM2. Instead of RD, we have 1 by GM2. Let's solve a problem now. Determine the voltage gain of the circuit if lambda is equal to 0. In the circuit, we do have an RD. The extra thing we have is instead of RS, we have a diode connected load. How is this diode connected load? You can see the gate is grounded, drain is also grounded. So technically they are shorted, which means this is a diode connected load, which means we can model it as a resistor whose resistance is 1 by GM2. Lambda is 0, so we do not have to consider R0. Let's remodel the circuit like this. Let us find the voltage gain. What we have over here is basically just a common source amplifier with degeneration. We have already seen the derivation for the voltage gain. Voltage gain will be RD divided by 1 by GM plus RS. Here we have RD, so RD will be the same. 1 by GM, we are talking about the transconductance of the transistor over here, M1. So we will call it 1 by GM1. Instead of RS, what we have over here is 1 by GM2. So the gain is going to be negative of RD divided by 1 by GM1 plus 1 by GM2. Finally, let us discuss some biasing techniques. We'll see fixed bias, voltage division bias, and self-bias. Fixed bias is what we have used in the entire video. This one. We add a fixed bias voltage V0 in series with the input voltage. In voltage division bias, we take the circuit and add a voltage divider like this. We have VDD here. It will be divided between R1 and R2. Out of that, whatever is dropped across R2 is the potential we get at the gate. So the bias voltage here is going to be R2 divided by R1 plus R2 multiplied by VDD. In self-bias, this is what we do. We take the circuit, a resistor is connected between the drain and the gate like this. We call it RF for feedback resistor because basically we are taking some potential from the output and feeding it back to the input. So technically the resistor is giving a feedback, so we call it RF. I'm sure you can figure out how voltage gain and impedances change using small signal models. So we have done the same thing in BJT amplifiers also. Let us move on and solve a problem. Determine the voltage gain and input impedance of the circuit if lambda is equal to 0. What we have is a common source amplifier with degeneration and a bypass capacitor. It has voltage divider bias. Input resistance is also included. As always, the first thing we need is the small signal model. Let us start by taking the small signal model of a MOSFET. At the gate, we have R input and then V input. At the drain, we have RD that goes to the AC ground. R2 is connected between the gate and the ground. In the small signal model, R1 will be between the gate and the AC ground. Now, assume that the potential that we get at the gate finally is Vx. Since what we have over here is a common source amplifier, we know Vx will be multiplied by minus GMRD at the output. But Vx is not our input. Our input is Vin. So we have to find out a relation between Vin and Vx, which is very easy. But before that, we have R1 and R2 in parallel with each other. Let us make it simpler and replace them with a single resistor whose resistance is R1 parallel to R2. Now we can clearly see that Vin is being divided between Rin and R1 parallel to R2. Out of that, whatever is dropped across R1 parallel to R2 is Vx. So Vx is Vin divided by R1 parallel to R2 plus Rin multiplied by R1 parallel to R2. If we take output over here, we already know output is going to be Vx multiplied by minus GMRD, or Vout by Vx is going to be minus GMRD. But what we want is the ultimate gain, which is Vout by Vin. We can write Vout by Vin as Vout by Vx multiplied by Vx by Vin, because then Vx and Vx is cancelled and what we get is Vout by Vin. We already know V out by Vx is minus GMRD. From here, we can write Vx by V in. It will be R1 parallel to R2 divided by R1 parallel to R2 plus R in. So this is what we get. V out by V in is minus GMRD multiplied by this much. That is our voltage gain. We also have to find out the input impedance. Since we have a dependent current source, we have to shut down all the independent sources, which means V in will be shorted and this point will be grounded. Now, since what we have to find out is the input impedance, we have to add a Vx at the input and find its relation with the current Ix. This is pretty simple. You can see the current Ix will flow through R in and then R1 parallel to R2. So the equivalent resistance there is Rin plus R1 parallel to R2. Vx by Ix is going to be Rin plus R1 parallel to R2. And that will be our input impedance. So that's all about it for today. See you in the next video. And please don't forget to subscribe.